All right, looks like we're live. Hello, everyone. Welcome. Thank you for joining us tonight. So I'm very excited to be here on behalf of Chegg. This is going to be a linear algebra live office hours. So my name is Joe. I am currently a fifth year PhD student at NYU in New York University. And I've TA'd for a couple classes here at NYU, and one of them is linear algebra. So this semester, I'll be here every week, Monday at this time, 7 p.m., to help you answer your linear algebra questions. So you should think of this as a time that you can pop in and pretend it's just like office hours. So bring your questions. You can type them in the chat, or you can just pop in and listen to me solve practice questions, answer other people's questions, and hopefully it'll be helpful. And if you've been to one of these live events before, welcome back. Otherwise, hope we'll have a great study session together. I've got my tea ready, got my tablet ready, and we can get started. So I will start us off with a practice question that I've prepared that I think highlights what you should expect to be knowing or learning at about the first or second week of linear algebra. But as I mentioned, you should feel free to type your own questions in the chat, and I will be able to see them and I can answer your specific questions. Okay, so the first question to go over is solving a system of equations using a method called row reduction. So this is not a new type of question. Perhaps before this class, we've already seen solving algebraic equations, but the point is we want to solve them in a systematic way. And this is using something called row reduction or Gaussian elimination sometimes. So the way that we do this kind of question is we first translate this into a matrix. So a matrix is a grid of numbers, and eventually in the class, it becomes, it captures more information, but for now, it's just another way to represent this system. So I'm going to take the numbers I have above. Actually, let me make it a little bigger. I'm going to take the numbers I have here above and just put the coefficients into columns. So I look at everywhere where there's an x, here, here, and here. And I'm going to write the numbers in a column, and same for all the other variables. So I'll start a second column for the y variable, and then a third column for the z variable. And then on all the way to the right, I'll put the numbers that have no variables. So on the other side of the equation, I have 6, 14, and minus 2. And then typically, you denote that that's the other side of the equation with a dotted line. So all I'm doing is putting the numbers of my equations into a grid. And you can imagine if you were going to solve the equation above, there are some things that you can do to manipulate them that won't change the answer. For example, if I can multiply any of the equations by, say, 10 or 7 or any number, and it won't change anything. So this is one thing I'm allowed to do. I'll say allowed manipulations. One is I can multiply any row by a constant. And then another thing I will be allowed to do is subtract equations from one another. So I can subtract equations or rows, equations/rows from one another. Okay, so if you notice, an equation above corresponds to a row in the matrix. right? Say the first equation, x plus 2y plus 3z equals 6, I represent with the first row, 1, 2, 3, dotted line, 6. And what is the goal? The goal with row reduction, is to simplify the matrix into essentially as close as we can, just a bunch of ones and zeros. So to make this precise, I want each row to have the first number be a 1. And so each row will then, if I have this, each row will have a first number, which I call a pivot number. And then the other condition I want is that in each column that there's a pivot, to be a 1, and I'll call this a pivot. And then in each column with a pivot, there should be no other numbers besides a 1, besides that pivot. Okay, so this may sound strange if you've never seen it before, but let's work it out with this example and we can see how it works. So in this matrix, I'm already starting off with the first row. It has a 1 in it. So there's nothing I need to do there. But then in that column, I would like to change this, this 2 here and this 3 here to just be zeros. And you can pause for a second. Why would one might want to do that? If you look at the original equation I was solving, this is kind of like eliminating the x variable, right? So if you were just trying to solve these equations without any kind of matrix thing, that's probably what one would do when you take algebra and whenever you take the class. If you want to solve some equations like this, you might want to try and eliminate one of the variables. So we're going to use these manipulations that were allowed, multiplying and subtracting, to do that. Okay, so let's do that. So the first step, I'm going to take the second row and I'm going to subtract the first row twice. So row 2 minus twice row 1. And what do we get? Well, the third row is going to stay the same. So let me quickly write that down. And the first row is also going to stay the same. And so now in the second row, I'm going to subtract the first row twice each time. So for this entry, 2 minus 2 times 1 is 0. And then for the second one, I have this entry will come from minus 3 minus twice the first number. So minus 3 minus 4, which is minus 7. And then similarly here, I'm going to start with 2, the original number in that row, and I'm going to subtract twice the first number in that row, in that column, sorry. So minus 2 times 3, and you get minus 4. And same thing here. Lastly, here we have 14 minus 2 times 12. Or sorry, 2 times 6, which is 12. And you get 2. Okay. So now I've gotten rid of this before it was a 2, and now I've changed it to 0. So it's like in that equation, I've eliminated the x variable. And I'm going to do the same thing again for the third row. So with a little less detail this time, since it is the same, I have the third row, row 3, minus 3 times the first row will get me, the first 2 rows will stay the same. So let me copy those over. So now I have 3 minus 3 is 0. 1 minus 6, because 2 times 3 is 6, is minus 5. And minus 1 minus 9 is going to be minus 10. Minus 2 minus 12. Sorry, minus 2 minus 18 is going to be minus 20. Okay. So I've successfully eliminated the x variable in these two equations. So if we pause, we can. Okay, so up here we went from a system of equations to a matrix. We can pause and see how that corresponds here. This corresponds to the system of equations, which is x plus 2y plus 3z equals 6, minus 7y minus 4z equals 2, minus 5y minus 10z equals minus 20. So anyways, there's some calculations here, but I want to impress the point that these matrix manipulations is just another form in which you would have done the algebraic manipulations with the equations over here. So it may look new, but it's actually just a new way of writing an idea that you've seen before. Okay, so let's continue. It looks like the easiest way to go on here. I'll draw an arrow. Let me just divide the last row by minus 5, just to simplify things. Zero, minus 7, minus 4, 2, 0, and then 1, 2, 4, right? This is okay. And oh, looks like, let me erase this for now since it looks like I'll need the space. Okay, so continuing. Now I have another 1. I'm going to swap the second row and the third row just so I can keep each one as higher. There's this doesn't have that much meaning, but it will just make things more systematic. So here I'm going to swap R2 and R3. Also, I see a question from Instagram. Could you show dividing with 4 numbers? I'm not exactly sure what you mean by that question, but when you multiply or divide, you would multiply or divide the entire row. So let me say something and perhaps it will answer your question. If not, you can try to rephrase and ask again. But the point is, if I have an equation like this, here's something I would not be allowed to do. I wouldn't be allowed to, say, divide just one of the numbers. So I wouldn't be able to say this is the same as y, say, just dividing the first one by 5. So I get y minus 10z equals minus 20, right? That is going to change the answer to the equation. So every time I multiply or divide by a number, it would have to be the whole row at a time. Yeah, but that may not have been actually what your question was. So feel free to ask a follow-up question. Okay, in the meantime, I'm going to continue writing out the solution. So here I'm going to, now I want to eliminate this minus 7. This is like eliminating the y variable from that row. So let's do that. How do I do that? I'm going to use the second row and add it 7 times to the last row. So the first 2 rows will stay the same. And okay, so here I'm taking the last row, R3, and I'm going to add 7 times the second row. So this becomes a 0, and then I have minus 4 plus 14, which is 10. Then I have 2 plus 28, which is 30. And similar to before, I'm going to now divide the whole last row by 10. To get 1, 2, 3, 6, 0, 1, 2, 4, 0, 0, 1, 3. Okay, so I want to pause again and see what equation does this represent. This is the same as x plus 2y plus 3z. The dotted line is an equal sign, 6. Then I have y plus 2z is 4, and I have z equals 3. So you can kind of see that through these matrix manipulations, the system of equations that I've ended up with is a lot easier to interpret or to solve from here, right? Because I've already solved for the z variable. And you can also imagine it's easy to then use z equals 3 and plug it in to the second equation to then solve for the y variable. Right, you plug in z equals 3 to the second equation, you get y plus 2z, y plus 6 equals 4. Then you can solve for y. Then you could plug it back into the first equation. So in a sense, we're already done, but we may as well finish this and do what I just said in the matrix world. Okay, so now I'm going to go back and eliminate this 2, which is doing in the matrix exactly what I just said in the equations. So I'm sorry for keeping erasing things. I'm going to take the second row and subtract the third row twice to eliminate that 2. So row 2 minus twice row 3. And I get 1, 2, 3, ... 6. The last row I'm not changing. But here in the second row, I get 0, 1. Okay, and then 2 minus 2 is 0, as desired. And then we have 4 minus 2 times 3 is minus 2. Okay, so here we have y equals minus 2, z equals 3, x plus 2y plus 3z equals 6. And we're almost done. To finish it off, I just want to subtract the second row use the second row to eliminate this 2, and then use the third row to eliminate the 3. So I'm going to take the first row, I'm going to subtract twice the second row, and then I'm going to subtract 3 times the third row. And let's see what I end up with. So the second and third row I'm not touching, and the first row, I'm going to subtract twice the second row, which eliminates this 2, and I'm going to subtract 3 times the third row, eliminating that 3. And what do I get here? I get 6 minus 2 times negative 2 is what I've subtracted, and minus 3 times 3. And let's see, what is this? This is 6 plus 4 is 10, minus 9 is 1. So I end up with x equals 1, y equals minus 2, and z equals 3. Which is now still technically a system of equations, but now it's also just the answer. So hopefully, I don't have an answer key in front of me, but hopefully I did the arithmetic correct so that this is the answer. But what I just want to impress upon you all is that these manipulations with the rows in the matrix is the same as if you just started out in Algebra 1 and you wanted to solve equations by what you usually say substitution or by elimination. This is the same thing, but what the point of this is you can do it in a systematic way. So for example, if you had 10 equations with 10 variables, this would get very out of hand if you were to try and write it out yourself. And what these manipulations serve as is a systematic way of doing it. You can imagine almost if you were to try and write code to tell a computer how to solve this problem. This is essentially what you would be doing. Okay, so that's it for the first practice question. This was the question, and this was the final answer. And for everyone who is also just joining us, I'd just like to take a pause again and welcome you. This is currently, we're having a live linear algebra office hours where you can pop in, either listen to me answer questions, or feel free to type your own questions in the chat. Let's see. Okay, so here's a question from Jasmine on TikTok. I wonder if computing determinant of AX over determinant of A, determinant of AY over determinant of A, etc. would have been faster. Yeah, so I wanted to, well, whether or not it would have been faster, in a sense, I would argue if you do this a lot of times, this becomes not too slow. But I also wanted to stick today with what people typically are learning in the first or second week of linear algebra. So there's a concept of determinants later, fast forwarding probably towards the end of a first year class in linear algebra. That's an alternative way of solving these equations. But for the next few weeks, well, I would say that also, as we may or may not get to today, doing this process of row reduction doesn't just give you the final answer, but okay, in other examples, you can see how it also gives you information about the geometry of these answers. So what I meant by that is here the solution is just a single point, x equals xyz equals 1 minus 2 3. You can imagine plotting this in a graph. There's other systems of equations where the answer has a more complicated geometry. Okay, so for example, what does x plus 2y plus 3z equals 6 represent? If you were to try and graph this on a XYZ coordinate system, it's a plane. So actually, this is pretty helpful. So maybe let me draw this out. Right, a system, an equation here. Well, okay, it's not obvious why, but I'll tell you that an equation like x plus y plus z equals 1, it looks like a plane. So it's hard to draw in 3D, of course, but you can imagine it looks something like that. And if I want to solve for two equations, so I'm just going to write some random numbers here. This would be like another plane. Let me change colors. And so if this was my system of equations instead, my answer wouldn't just be a single point, but it would be a whole line of solutions, which is hard to see, but I wonder if this helps any visualization. If you take like two sheets of paper and you cross them, they'll intersect in a line, right? So actually you'll get a whole line of solutions. And this row reduction process not only gives you the answer, but it gives you that characterization. So maybe we'll get to an example where we see that today. Also from B on TikTok, how do you get the 2z? Oh, I'm afraid maybe this is, let's see if I can see the 2z. Oh, perhaps the question was on this step. Okay, well, I'm gonna assume I did the arithmetic correctly. This 2z here is just how you interpret what is this row. So each row in this matrix is going to represent an equation where the first column is going to be my x variable, the second column is going to be the y variable, and the third column is going to be the z variable. So you see here, this column 3, 2, 1 corresponds to the z variables in my equations. On the other hand, if the question were how I got a 2 over here, I guess, yeah, I think that was right. That step was right. So I took this whole row and I divided by -5. Yeah, so maybe the question was here, how I got this. And it's how I interpret this row by taking taking the numbers as like my coefficients. And each column will correspond to its own variable. So I don't know, hopefully that doesn't sound too complicated, but I think this example which is why I tried to write out these 3 examples, should be illustrative of how to go back and forth between a matrix and the equations. All right, so you can stare at this and see how they correspond. Okay. If no one has, you can feel free to ask your own homework question if you'd like as well. I don't have to be going over my pre-prepared questions. But otherwise, for now, since we were on this topic here, let's do an example that is like that, which happens to be the next one I prepared. So that's great. So here I have another system. So put a question, and let's go through the answer. Oh, okay. So from TikTok, there's a question. Could you summarize what a matrix is? I would say that if you're taking linear algebra right now, for roughly the first half of the class, a matrix is just going to serve as a way to represent a system of equations and nothing more than that for now. So here I have equations, and I'm just going to put them in this grid. And as long as I remember how to go back and forth between them, you see that they really capture the same amount of information. Yeah, but then there will be a certain point in the class where you start to view a matrix as more of a transformation. And maybe I won't speak too much on that today. There's a question from Alkazam on TikTok. What's the real world representation of an eigenvector? Like, what is its function? Okay, this is a little specific, I think, to you maybe, since in general, eigenvectors are later in the class, but let me try and answer this. So, first of all, my expertise is not in applied math. So for real world function, it would take me a little bit to get there. But at least for the theory of a matrix, you should think of I'm assuming since you're asking the question, you have some familiarity with how a matrix is viewed as a transformation. You should think of an eigenvector as special vectors where the action or the result of the matrix applied to that vector is just abnormally simple. So as an example, a matrix can rotate vectors, stretch them, and do a combination of them, and maybe flip them. But there are certain vectors where the action is just very simple. It just stretches the vector along that line. And so what the eigenvectors do is you can basically pinpoint the key effects of how the matrix acts on the vectors, just by studying this action just on a few vectors, namely the eigenvectors. And in practice, if you are wanting to say, okay, so if you want real world, I will say a real world application rather than a real world representation. Sort of a lot of key information about the size of the matrix will be contained just in how it acts on the eigenvectors. So yeah, maybe that's as much as I can say for that. But yeah, these are great questions. I'm glad that we have questions coming in from the chat. Okay, so let me come back down to perhaps week 1, week 2 of linear algebra, and I'm going to solve this equation. So first thing, again, is I want to represent this as a matrix. How do I do that? I want to plot the numbers in a grid in a way that each column corresponds to a single variable. So first, I'm just going to rewrite the system of equations so that, for my own visualization, all the variables are actually stacked together in a column. So here I have 2x plus y plus 12z equals 1. And I'm going to move the 9z over here over to the other side, just so when I can write it in a column, they really represent the same variable. Plus 9z equals minus 1. And now I'm going to put it in a grid again, just as before. This is just, if I wanted to represent this as a grid of numbers, I would write this. 2, 1, 12, a dotted line for the equals. 1, 2, 9 equals -1. So I'm going to do the same thing. I'm going to attempt to have each row just begin with a 1 and then try and eliminate everything else in that column. Okay, the easiest way to do this is to just swap the two rows. Then I can start with a 1. So I'm going to swap row 1 and row 2. I will say that the point of swapping doesn't actually do much, right? If you imagine these are a system of equations, just changing the order that I write the equations isn't doing anything. It's more just, honestly, it's more just that it looks nice if all the ones are in a slant like that. And the actual reason is that I like to have the reduced form be unique. But this doesn't have as much purpose as the other manipulations. Okay, so I'm going to take the second row, subtract twice the first row. And we get 0, 1 minus 4 is -3, 12 minus 18 is -6, and 1 minus -2 is 3. And then I'm going to divide the second row by -3 because I want a 1 to be the first number in the row. So the first row remains untouched, and I get 0, 1, 2, -1. And that's all my rows. So now I'm going to look at each column with what I call a pivot, but is these ones. And I want to make that the only number in that row, in that column. So it's already this case for the first column. And I'm going to make it the case for the second column as well by taking the first row and subtracting twice the second row. So I'm not touching the last row. And here I have 1. Okay, 2 minus 2 is 0. 9 minus 4 is 5. And -1 minus -2 is 1. So let's see what I get here. I look at the equations that this represents, and I get x, the first column is x, plus 5z equals 1. And then I get y plus 2z equals -1. And that's as much as you can simplify this. And so this might not seem solved, but let me show you how this really is just a clean representation of the solution, actually. So what I can do is this extra variable z, I'm going to call a free variable. So in the matrix, this is a column with no pivot. So let me write column with no pivot is what we call a free variable. And I'll come back to that terminology in a second. But first, I'm going to move all the free variables to the other side. Okay, so this is the same system of equations as saying x equals 1 minus 5z and y equals -1 minus 2z. And once I move, okay, so maybe I should write down here. To go from here to here, I move, let me scroll, free variables to the other side. And now what this solution means is I can pick any value for z, say 7 or 13, anything I want, 25. I plug in that value for z, and I can solve for x and y, and this gives me a solution to my original equation. So let me write that down. From here, we can plug in any value for z, then solve for x and y. Let me try and move this. Is this how this works? This app? Okay, great, it is. So what's an example? Okay, I can plug in example. Plug in, I don't know, let's say z equals 3. Why not? I get x equals 1 minus 16, or sorry, 1 minus 15, so minus 14. And y equals minus 1 minus 6 is minus 7. So solution, or I should really write to be, actually, let me move this over here for a second. So one solution is minus 14, comma, minus 7, 3. Okay, we can also plug in z equals 1. We get x equals minus 4 and y equals minus 3. So another solution is minus 4, minus 3, comma 1. So what's going on here is there's actually infinite solutions to this system of equations. There's a whole, well, if you were to graph it, you would see there's a whole line of solutions, just like we drew up here. Here we also had 3 variables and 2 equations. And visually, okay, it's always hard to draw in 3D, but hopefully visually you would see it that the intersection between these 2 planes is a whole line. Well, right, the planes would go on infinitely, but I drew them as rectangles. And so the reason that z is called a free variable is that I can choose any value for z, any real number I want, and then I can plug it in to my my equations here and get a solution. One thing I would clarify, or no, actually first let me, just to connect this to something I was saying before, is that here in my row reduction process, at this point, before I even know what the solutions are, I can say that, okay, here's one column with a pivot, and here's another column with a pivot. But here I have one column with no pivots. So none of these ones with a 0 all around them. Perhaps not obvious, but I can claim that just by this information, the fact that there is a free variable, a column with no pivots, the geometry of the solution, first of all, there will be infinitely many solutions. And second of all, if you were to graph this, it would look like a whole line of solutions. from TikTok, is there a way to check these solutions by substitution? Yes, let's do that. So here is what I claim to be is a solution. X, Y, Z is -4, -3, 1. Let's see if we can plug that in and check that it really does solve this. And this will be the test for me, since I don't know right now if I did everything correctly, but let's hope that I don't embarrass myself here. So here I'm checking, checking X, Y, Z equals, what did I say? -4, -3, 1 is solution. So I'm going to plug it in first to the first equation. I get -8 -3 plus 12 is 1. So that's correct. And then in the second equation, I have -4 -6 equals -1 -9. What I'm doing, by the way, if this isn't clear, is I'm just plugging in my solution to these equations. And this is also correct. Again, -10 equals -10. So yes, you can always check these solutions. Actually, if you are doing your homework, or if you have extra time on a quiz, I would recommend checking the solutions. Just go back to the original equations and plug it in. This will let you know whether or not you made a calculation mistake somewhere along the line. But yeah, that's a great question. Thank you for that question. Let's see, anything else to say on these types of questions? Yeah, okay. So let's see, we've got about 13 minutes left. I'm going to try and illustrate one final point. So not this one. I think it's important to see, so we've seen two cases so far tonight. We've seen in this question, there's a case where there's exactly one solution, right? We saw that here. There's just one answer. X equals 1, Y equals -2, Z equals 3. Hopefully, if you plug that in here, you would check and see that it works. We've also encountered a case where there's infinite solutions. And this is characterized by the existence of a free variable. So once there's a column with no pivots, then you know there's going to be infinite solutions. And I want to do an example where you actually have no solutions. Unfortunately, I've erased the question, but it shouldn't be too hard to write one. Yeah, okay, so let's say here's another question. I have x plus 2y equals 6. And then I have 2x plus 4y equals 10. And maybe the question is, solve this system, which is a little misleading. I'm telling you guys that here's an example where there's no solution. And perhaps you can stare at this and see why that might be the case, but let's write it out in a matrix, because this is important. So what I have, okay, let me write this. 1, 2, dotted line for the equal sign is a 6. And then I have 2, 4, and 10. And so, okay, here I have a 1, and I want to make the number below it 0. So let's do that. How do I do that? I will take the second row and subtract twice the first row. I'm not touching the first row, so I'll copy that over. Then here I get 2 minus 2 is 0. I get 4 minus 4 is also 0. And here I get 10 minus 12 is minus 2. Okay, I suppose what I could also do here is divide this last row by minus 2 to make it a 1. But let me stop here and say that, okay, technically, there's two ways to think of this. One is that this last column has become a pivot column. So this last one, okay. Oh, okay. Well, I think I'm having some technical issues on my side with Notability, but I think what I want to say is I don't have to write anymore anyways, which is that here there is a row with all zeros and then a number at the end. So all the variables here are a 0, correspond to a 0. So if you can imagine, sorry, I'm not writing this out, but if you can imagine, when I translate this back to an equation, what equation does this represent? Okay, the first one, I didn't change anything. It's the same as above. X plus 2y equals 6. Whereas the last equation, it corresponds to 0 equals minus 2. Well, that has no solutions, right? Clearly, nothing I can do will let me solve 0 equals minus 2. And that means that this system has no equations, no solutions. And I would also highlight, it's important to know that somehow this is the only thing that can go wrong. The only way that a system can have no solutions is if when you do this reduction, you end up with a row that looks like what I have here. 0, 0, 0 all the way. And then at the very end, I have just a non-zero number, like minus 2. So firstly, the reason that means no solutions is that the equation it represents is just 0 equals minus 2. But also, that's the only thing that can go wrong. So the exact condition to know when a system has a solution or not is just to check whether you find something like this. All zeros followed by something else at the end. Okay. So we're almost out of time, but maybe before, well, of course, you can still feel free to ask questions in the chat, but let me summarize these 3 questions that I went over today. The first, well, okay, all 3 fall in this category. You're given a system of equations, of linear equations, and you want to know, are there solutions? And if there are, I would like to solve it. So we do that by writing the equation in the form of a matrix. You know, for now, this is just another way to represent the system. And we do these row manipulations called row reduction. It's just a systematic way of adding and subtracting the equations, just as you would in Algebra 1 when you want to eliminate variables. But once you do the row reduction, you can have a couple of things, 3 things can happen. One is you have these, the left side will just look like this, a diagonal of pivots. This is when you know there's only one solution. Another thing that can happen is you do the row reduction and you get something like a 1, 0, 0, 1, but then you have an extra column. This extra column tells you that you're going to have infinite solutions. So here we saw that there's a whole line of solutions. You ended up being able to plug in any value for z, and you can get any solution. And I really like what the person in chat mentioned, that you can, or they asked that you can, and you should, if you have the time, plug in one of these solutions back into the original equation just to make sure you've done it right. And then the last thing that can happen is if you have all zeros followed by a non-zero number. And you should just remember that this corresponds, what does it correspond to, is on the left side I have 0, and on the right side of the equation I have -2. So there's no way I can solve 0 equals -2. And so, yeah, that is just about it for today. I think since I'm also having a technical issue on my side, I'll stop there in terms of writing. And yeah, I just want to give a thank you to everyone who is joining. We'll be back every Monday at this time, so 4 p.m. Pacific time or 7 p.m. Eastern time for 1 hour on linear algebra. I will try and prepare questions each week that go along with what I expect a typical first-year undergraduate class to be going at that pace for linear algebra. But you should think of it as an office hours. So if you have your own questions, of course, feel free to type them in the chat. Ideally, I'll be able to get through all of them. Otherwise, you should make sure that you can check out the survey at the end, and that feedback will be very helpful for me and for the Chegg team. Otherwise, you can follow Chegg on TikTok, YouTube, Instagram, I believe also Twitch for these live streams. And yeah, thank you for coming. Yeah. Also, I guess there's a question, if we're still live, from Nightbot. What is the toughest class you're taking? Well, as a PhD student in the later years, I'm not really taking any classes. But I would say probably the hardest class I ever took as an undergraduate was a math class called differential geometry. That class, I feel like, really killed me in my undergrad. And I feel like even today, it is made the subject of geometry a little, there's a huge mental block for me personally. But yeah, I know that for a lot of people, the hardest math class for them ends up being linear algebra. So I hope that these live office hours can be a help to you throughout the semester. But, of course, Chegg also has other resources, and, we'll be here throughout the whole semester and hope that we can help you all out. Yeah. All right. Well, that'll be it for this week.